This is the derivative action. And again, for simplicity, we are considering Gm equal to Gf equal to 1. For simplicity, again, we are considering Gm equal to Gf equal to 1. Now, let us substitute all these 4 individual transfer functions in the closed loop transfer function equation, which I have included at the top. So if we substitute all individual transfer functions, we get this closed loop transfer function, CLTF. After rearranging, we get equation 14. After rearrangement, we get equation 14. So, is there any change of order, student? We have started with first order process. We have started with first order open loop process. We have ended with first order closed loop process, equation 14, you see. I repeat, we have started with first order open loop process, that is Kp by tau Ps plus 1. And we have ended with equation 14, that is also first order process. So there is no change of order. So that's why our first remark, you see, first order process, that is plus derivative controller, and it yields first order closed loop process. So order does not change. Second remark is this one. In equation 14, we got tau p prime equal to tau p plus Kp Kc tau d. And in this equation, all the terms are positive. All the terms in the sense, if you consider Kp Kc a combined term, then all the terms are positive. Tau p prime, tau p, tau d, they all are positive, and Kp Kc also positive. So if that is the case, then tau p prime is greater than tau p. If that is the case, then tau p prime is greater than tau p. Fine. So it means that the closed loop response becomes sluggish over the open loop response. And it is also obvious that if Kc increases and tau d increases, sluggishness further increases. We have considered Kc and tau d because these are controller tuning parameters. Fine. If Kc increases and tau d increases in this equation, we get higher tau p prime. That means sluggishness further increases. So can you tell me what is the value for offset? What is the value for offset for this case?
Sir, 0.
No.
Sir, 1 if we consider unit step
1.
change.
Yeah, it is 1. It is 1. What's your roll number? Adrija.
Yes, sir.
Who is the second boy? Someone else also told 1.
19CH3008.
Yes. So it is clear that offset is not eliminated by derivative action. Fine. Offset cannot be eliminated by derivative action. Now this we have discussed, effect of derivative action we have discussed for a first order process. Now let us extend this concept to second order process. I repeat, we have discussed the effect of derivative action for first order process. Now we are extending that concept to second order process. And first equation is CLTF, closed loop transfer function. And we have then substituted all individual 4 transfer functions with GF GM equal to 1. Then you see the final expression we get for second order process. This is the final expression. Okay. This is the final expression we get for second order process with derivative action, assuming GF equal to GM equal to 1. Now similarly, we want to make a couple of remarks based on this. Again, same remark, no change of order. You see, this is also a second order transfer function. This is also a second order transfer function, and therefore there is no change of order. Not only that, you see our tau also does not change. This is tau square a square. In fact, in the open loop process also we had tau square a square, you see. So this tau does not change. And you know the effect. And third one is this one. You see, I have just compared two zeta prime tau equal to this one. In a third remark, I have written this one, 2 zeta prime tau equal to this expression. So again, you see in this expression, all are positive, provided KPKC we have considered a combined term. Okay, that means for the closed loop process, we are having more zeta. So after including the controller, we are getting sluggish response. So it is just reverse compared to proportional action and integral action. Earlier we have seen that if we increase Kc, we get faster response. But in this case, it is just reverse. So I can say like this way that if we increase Kc value, proportional action provides faster response. Integral action also provides faster response, but derivative action pulls back the response. I mean, proportional and integral action leads to 2 steps forward, but derivative action leads to 1 step backward. So it's a very conservative control action. And therefore, this term is written, you see, it provides robust behavior. I repeat, if we simply increase the Kc value, proportional and integral action lead to 2 steps forward. But a derivative action leads to 1 step backward movement. 2 step forward movement for proportional and integral action, 1 step backward movement for derivative action. So derivative action is a conservative control action, and therefore this term is used, robust control scheme. So this is all about the effect of 3 actions. Now we want to gist. I mean, why we are not going for only proportional action? Why not then integral action? Why we are considering PID? Because PID is complicated, and if you buy it from the market, it is expensive also. Let us come to that point. Effect of composite control actions. We have finished all 3 individual effect of all 3 individual control actions. First, we have discussed effect of proportional, followed by effect of integral, and finally today we discussed the effect of derivative action. Now we want to just summarize the effect. I mean, how we are progressively moving, you see. If we consider proportional action, what is the advantage? It speeds up the response. It means if we increase the Kc value, we get faster response. Okay, this is the advantage, you can say. But what is not taken care of by proportional action? Offset. Fine. Proportional action speeds up the response, that is the advantage. But proportional action cannot eliminate offset, that is the disadvantage. Now we want to take care of this second issue. What we can do, student, if we eliminate the offset? What is your suggestion? Got my question? Proportional action speeds up the response, But drawback is it cannot eliminate the offset. So what action you were suggesting? Anyone?
Sir, integral action, we can.
Yes, integral action. Now let us go to integral action. So what it can do, it can offset eliminate. It can eliminate offset. This is advantage. But again, what is the drawback? If we add integral action, anyone? Order increases. Order increases means we get more sluggish response. Fine. So we want to eliminate offsets. For that, we can consider integral action. But there is a drawback. What is that? First order system, if we take plus integral action, our order increased by 1. And order increases means sluggishness increases. So what we can do for this? If the response becomes sluggish, we want to speed up again. So we have two keys. One is either we can increase Kc or we can decrease tau I, because tau I is present in the denominator, or both. But in that case, we may have instability problem. I hope you understood this. If we want to eliminate offset, we can add integral action. If we add integral action, we face this drawback. Order increases. Order increases means sluggishness increases. So how we can overcome this situation? Either we can increase Kc or we can decrease tau I, or both. But if they are sufficiently large, reasonably large, we may have instability problem. So how to come out from this situation? We need a robust situation. So for that, we need derivative action. To take care of the issue, instability issue, we need to add derivative action. So just now we discussed derivative action improves robustness. Okay, but what is the drawback? Derivative kick. The drawback of derivative action is derivative kick. Any solution, student? How to take care of this? Anyone? How to take care of this issue, derivative kick? Just recall, we discussed this. We can add one filter to make the controller proper. To make the controller, particularly the derivative term proper, we need to include one filter. That's it. If you have any question, you can ask me. So this chapter we finished. If you have any question, doubt, you can ask me. Otherwise, we'll go to the next chapter. You note down this exercise problem. So in the second problem, only difference is that we have considered, it is suggested to consider PI controller. So far we have discussed all individual control actions, proportional, integral, derivative, individual actions. But here it is PI controller. This is the only difference. Okay. So far we have considered the controller equation as proportional controller or integral controller or derivative controller. Here the combination of P and I is suggested to consider. Okay. Any question, anyone? No. Okay, let us go to the next chapter then. Yeah, this is our next chapter. We want to discuss stability. In our next chapter, we want to discuss the stability of the feedback systems. See, we have discussed this stability before. If you recall, we have discussed qualitative analysis of this stability. We have considered two distinct real poles. We have considered two complex conjugate poles. We have considered multiple real poles. I think you can recall this. But that stability analysis we did for open loop process. Now we want to perform the stability analysis for closed loop process. I mean with controller. Fine. Before we have discussed the stability analysis through this title like qualitative analysis, stability analysis. There are different kinds of routes we have considered. Like I have given the just now example. Two real distinct poles, multiple real poles, conjugate poles, and pole at the origin. But that stability analysis we have performed for open loop process. There was no controller. But now we want to discuss the stability for closed loop process with controller. Fine. So this is the definition. A dynamic system is said to be stable if for every bounded input it produces a bounded output, regardless of its initial state. And if this is not followed, it is called unstable system. So this is basically the bounded input always remains between an upper and lower limit. Can you give any example, student, of bounded input? We have considered several forcing functions like step, pulse, impulse, ramp, sinusoidal, which are under this category, bounded. Anyone?
Sinusoidal.
Yes, sinusoidal. Step is also within this.
Yes.
But not the ramp.
So pulse.
Yeah, pulse is step basically, no? Pulse is basically two steps. It is a summation. It is basically we get by summing up two steps. But not the ramp, you know. Here I want to mention another important issue that unbounded term. This unbounded only exists in theory, not in practice. Because your understanding all physical quantities are limited. Suppose we are considering a pipe. So a pipe, we can consider either 0% or 100% flow. Fine. It cannot be infinite quantity. It's not possible in practice. If we consider a valve, it's minimum 0% opening, maximum 100% opening. We cannot entertain more than 100 or lower than 0 because it has certain physical limitation. So therefore, this unbounded term does not exist in practice. But in theory, we can consider this. The same thing is applicable for input also. It's not only output. It is also true for input. Let us consider two different cases, you see. In the left hand side, what is shown, it is a stable response because you see this amplitude is gradually decreasing. Oscillation with decreasing amplitude in the left hand side. Thus, it is stable response. In the right hand side, there are two categories. One is oscillation with the growing amplitude, and another one is monotonic case. Both are unstable. Oscillation with increasing amplitude in the right hand side, as well as monotonic instability are shown. Fine. So these are the typical cases. Now, what I want to mean by this, you see, this is the actual case I want to mention here. We have a process, and in the input section, you see this is the input. The C lies in between C max and C min. So if we have bounded input and it is introduced to the process, we should have bounded output. Then only we can say that it is a stable process. Simply you can note down like this way. We have introducing a bounded input or change in the input variable within certain bound. Then the process should provide the output within the upper limit and lower limit. So this is one case. I mean, stability we can define like this way. Another way, as I told, that first in the case of open loop system, and in fact just now I told for the open loop case, which we have already discussed, it is stable means all the poles are located left to the imaginary axis. Fine. This one in fact we have started, we have discussed. Another way we can define the stability in this way. An open loop system is said to be stable if all the poles are located left to the imaginary axis. One example is also given here, you see. Gp equal to Kp by tau Ps plus 1. Time constant is always positive. So therefore, it's a stable system. Now, how we can extend this to closed loop system? Yeah, we can extend to closed loop system. You see this? So for the open loop system, as I mentioned, transfer function is basically the ratio of two polynomials. If we consider numerator equal to 0, we get zeros. If we consider denominator equal to 0, we get poles. I repeat, for the open loop system I mentioned before, transfer function is a ratio of two polynomials. If we consider numerator equal to 0, we get zeros of the system. If we consider denominator equal to 0, we get poles of the system. So in a similar way, if we consider the denominator equal to 0, we get the poles of the closed loop system. Yeah, I am coming to that point, but before that you note down this. So this is the set point element, which we are representing or denoting by G suffix SP, and this is a load element, which we are representing by G suffix load. Now, like open loop system, for closed loop system also we want to consider denominator equal to 0. You see, that is considered here. For open loop system, we have considered denominator equal to 0. Same thing we want to do here as well for closed loop system. Denominator equal to 0. And this is popularly called as characteristic equation. You remember this term, we will extensively use this term in stability analysis. Just consider the denominator of the CLTF equal to 0 as characteristic equation. And here, this term, the second term, we consider as open loop transfer function, G suffix OL. This term is considered as open loop transfer function, G suffix OL. And remember, this open loop is a little different than the open loop we have considered so far. Why it is called so? It is explained here, you see. This GOL is basically YM divided by YSP. And YM we can only get if we disconnect here. Otherwise, it is always in the closed loop. This YM divided by YSP we get, you see, this is the output and this is the input. Then we get this. We are just multiplying all these four transfer functions. Since it is disconnected here, that's why it is called open loop. I will explain this issue again from a different corner later. You see, this open loop transfer function only depends on four individual transfer functions, GC, GP, GF, GM, but it does not depend on GD. It depends on the four individual transfer functions, GC, GP, GF, GM, but it does not depend on GD. And another remark is that the roots of the characteristic equation are also the poles of the CLTF. Thus, they are often called closed loop poles. The roots of the characteristic equation are also the poles of CLTF. Thus, they are often called closed loop poles. Fine. So let us come to discuss one example on this. You see, this is the example. See, our open loop process is unstable process, and we want to stabilize it by using proportional controller. Now, question is at what condition we can stabilize this process? I repeat the question. Our open loop process is unstable. To stabilize this open loop process, we are employing a P-only controller and finding the necessary condition for stability. Our open loop process is unstable. To stabilize it, we are going to employ a P-only controller, and then we are finding the stability requirement, the condition for stability. So you are understanding here pole is 1 positive, that means the system is unstable, as I told. Since pole is 1, S equal to 1, that means it is positive. So open loop process is unstable. It is very clear. This is the open loop transfer function, okay? GPM bar plus GDD bar. This is the open loop case. We did not use any controller so far. Now let us use one controller. So this is our P-only controller. For simplicity, we are considering GMGF1. And this is our closed loop transfer function. I have just substituted all these individual transfer functions in the standard CLTF equation. So all 4 individual transfer functions are known to us. Then I have just substituted in the CLTF standard CLTF equation here. So this is the pole, and it should be 0 for stability. Student, can you tell me what should be the condition in terms of Kc for stability? Anyone?
Kc greater than 0.1.
Correct. What's your number?
19 CH 30008.
So for stability, it must be greater than 1 by 10, you see. So you understood our open loop process is unstable. We are just employing P-only controller, and then we are making the system stable. This is the beauty of the controller. It's not only to provide the faster response, etc. Okay. The proportional controller, not only proportional controller, other controllers as well, they can provide stable response, but you have to fix this Kc value like this way. Okay. Now let us go to this Routh stability criteria. I think you note down the points. Routh or Routh test. Routh test or Routh test. It is a closed loop stability test. That means we need to consider the CLTF for stability analysis. Routh test is a closed loop stability test. So we proceed with CLTF, closed loop transfer function. An interesting point is that it's an algebraic test and it tells us how many roots are present in the right half plane without calculating the values. This is a interesting point. It tells us how many roots are present in the right half plane without calculating the values of those roots. And it is limited to polynomial equation only. So CLTF must be polynomial. It is true for polynomial equation only. So the CLTF must be polynomial. But suppose we have one, transfer function of an open loop process this way. First order plus date time system, you see. In one case, we have this first order plus date time. Okay. Now, if we want to get the polynomial equation, in that case, we need to consider Pade approximation for this exponential term. Then only we can get the polynomial. But definitely that is approximate polynomial. I repeat, suppose we have an open loop process and that is the first order plus date time. So to get the CLTF in the polynomial form, we need to do the approximation. We need to approximate this exponential term. Now how you can do that? We can use Pade approximation. Okay. So in that case, we can have the approximate polynomial. And then if we do this root test, that can, we can perform the approximate analysis. So what I want to say is that if your polynomial is the approximate polynomial, then we can perform approximate analysis. If our polynomial is the exactly polynomial, we can perform the exact analysis. But we can do. Come to the steps. So what steps we usually follow in case of root test? Let me give those steps. In the first step, you need to develop the closed loop transfer function. And in fact, for that, we need to know all individual transfer functions, GC, GF, GF, GM, and GD. So in the first step, you need to develop CLTF. This is a standard equation. And for this, you need to know all individual transfer functions. Total 5 transfer functions are there. In the second step, you write the characteristic equation in standard polynomial form. CE is basically the characteristic equation. In the second step, you need to write the characteristic equation in standard polynomial form. So this is the standard polynomial form, you see. Here A0, A1 to AN, these are coefficients, constant parameters. In the standard polynomial expression, A0, A1 to AN, these are coefficients. Now in the third step, not third, within this in fact, let A0 be positive. We are expecting that this A0 is positive. If it is not positive, to make it positive, we can multiply both sides by -1. I repeat, in equation 3, we want to see A0 as a positive coefficient. If A0 is not positive, to make it positive, we can multiply both sides of equation 3 by -1. This is the first test. After multiplying with -1, if A0 was not positive, you just inspect all coefficients in equation 3. If only one coefficient is negative, then at least one root of characteristic equation lies in right up plane. At least one. You remember this issue. Okay, I'll ask you this question again. Why at least one? And if all are positive, we cannot say still about stability. So we need to go for second test. If all coefficients A0 to A1 are positive, still we are not sure about stability. So we need to go for second test. So we do not have time, students. So what we discussed today, particularly this Ruth test, be prepared in the next class. I will ask you, because otherwise I need to start again from the beginning of the Ruth test. Okay, you go through this part on Ruth test, what we have discussed today. And in the next class, I will ask a couple of questions from here, and then we'll proceed from second test itself. If you have any doubt, yes.
Yes, sir. Like when would be the next week is the test window. So will there be a test conducted in the next week?
You decide. If you want, I can take. Otherwise, we may go for the test on last day, maybe Thursday. Okay.
So, sir, you will conduct it in next week, Thursday.
Maybe you decide. If you tell me on Monday, I can take the test. What is your?
Yes, sir. Could you take it on Tuesday, because we already have so many tests on Thursday? Next week, Tuesday would be a good time. I mean, if you can take it in the last 1 hour of the class.
Yeah, that is also possible. Can you give me other than these class hours? Maybe Saturday? Because we are lagging,
Yes, sir. I mean, some people might have CDC. I mean, they're having internship interviews, and also that might be the only issue of conducting it on Saturday.
Okay. And Sunday? Same thing.
Saturday and Sunday are packed with the interview.
Okay. I got.
Sir, can you take it on Friday?
Yeah, Friday is also possible.
Yes, so like Friday afternoon, we don't have any classes. So
yeah, no problem then. Basically, I have calculated we have almost 8 classes we are going to miss in this semester. 8. So 8, are you understanding? No? Who's saying we can cover 8 classes? So anyway, you decide and let me know in the next week. Okay, if Friday is okay to everyone, I do not have any problem.
sir, like you can take an extra class on Friday, but conduct the test on a class hour. Like
Oh, is it?
Yes, sir. Like Friday, you can take a 1 or 2 hours of extra class in the afternoon slot, and you can conduct the test in one of the class hours itself.
Yeah, no problem, man. No problem. It's okay.
Okay, sir.
So Tuesday is fine.
Yes, sir.
Yeah, then no problem. I will take on Tuesday. Okay.
Thank you, sir.
Yeah, thank you.